Good morning, everyone. My name is Neha Goyal. I'm the student of BSc Chemistry Honors Final Year. Today, in this video, I'm going to make a visual impaired video on the chapter Synthetic Drugs. In our day to day life, we come across many substances which have specific colors. In this unit, we will discuss what is color, how is it related to the constitution of the molecules, what type of color substances called dyes, natural or synthetic.
Various articles of daily uses. Color and constitutions. Color. When white light falls on a substance, three processes may occur. If the light is totally reflected, the substance appears white. If the light is totally absorbed, the substance appears black. If a certain portion of light is absorbed and the rest reflected, the substance has colored of the reflected light. If only a single band is absorbed, the substance has a complementary color of the absorbed band. If a substance absorbed all visible light except one band which is reflects, the substances will have the color of the reflected band. For example, it is evident from the above table that if a substance absorbs blue color, it will appear yellow, which is a complementary color of blue. In fact, no substance absorbs a single band, and hence no dye has a pure shade. For example, the malachite green predominantly reflects the green light, but also to small extent it also reflects red, blue and violet light. It may however be noted that substances which appears to be colorless also have absorption spectra. In such cases, absorption takes place in the infrared or ultraviolet regions, but not in the visible region of the electromagnetic spectrum. Relation between color and the constitutions. Many theories have been put forward from time to time correlate the color with the molecular structures. Some of these are described below. Witt's theory. In 1876, it was observed by Otto Witt and a German chemist that the intrinsic color of any compound is due to the presence of certain groups containing multiple bonds. These groups, which which impart color to a particular compound are called chromophores. Chromophores. Greek chroma, color word is forces, becoming and the compound containing the chromophoric group is called chromogenes. Some important chromophores are nitroso, carbonyl compound, para and orthoquinidide, ethylenic bond, acetylenic bond, benzene ring. Further, greater the number of such chromophores, deeper is the color. This is particularly marked when the chromophores are in conjunction with one another. For example, as the number of conjugated double bonds increases, the color of diphenyl C6H5 CH double bond CH and C6H5 depends colorless colorless, and when yellow and orange pale yellow shows color. Ethylene 1,3 butadiene and 1,3,5 hexatriene are colorless, but beta carotene has orange red color due to the presence of 11 conjugated double bonds. Beta carotene. Oxochromes Witt also observed that there are certain groups which themselves are not chromophores but depend the color when introduced into a colored molecule. Such groups are called oxochromes. For example, OH, NH2, NHR, NR2X, halide groups CO2H. Even alkyl groups exert weak oxochromes effect. Let us now examine the effect of oxochromes on the intensity of color. Both naphthalene and naphthol are colorless. 1,3-dinitronaphthalene is pale yellow, but 2,4-dinitro-1-naphthol is orange red. For example, naphthalene 1,1-naphthol, 1,3-dinitronaphthalene, 2,4-dinitro-1-naphthol. Thus, the presence of oxochromes, that is, OH group, has depended the color of 1,3-dinitronaphthalene chromophore from pale yellow to orange red in meretrice yellow. Two other terms which are also commonly used in connection with dye are bathochromic and hypsochromic groups, whereas bathochromic groups bring about the dipping. Hypo, Hypsochromic groups bring about the lining of color. In dye industry, deepening of the color means color changes from yellow to orange, orange to red, red to purple, purple to blue, blue to green, green to black. This is exactly the order of complementary color of the color observed. Absorbed, thus, when we say that the color of compound is deeper than the other, it simply means that the wavelength of maximum absorption of the former is longer than of the latter. Since visible color is the complementary color of the absorbed band, bathochromic groups causes red shift, while hypsochromic groups causes blue shift, etc. Modern theories of electronic theory of color. Two electronic theories have been proposed to explain the origin of the color. These are valence bond theory and the molecular orbital theory. These most important differences between valence bond and molecular orbital theories is that in the valence bond theory electrons are dealt with the pairs, but in MO theory they can be dealt with the singly bond. Valence bond theory. According to valence bond theory, the electron pairs of molecules in the ground state are in state of oscillation, and when placed in path of a beam of light, they absorb a photon of appropriate energy and get excited. The wavelength of the photon of light absorbed depends upon the energy differences between the ground and excited state. The smaller is the difference, longer is the wavelength of light absorbed. To illustrate VB theory of color, let us first consider a molecule of ethylene which may be regarded as a resonance hybrid of following two structures 1 and 2. To a first approximation, ground state is represented predominantly by structure 1, while excited state is represented by the structure 2. The energy differences between these two states is very large, and hence a photon of short wavelength is absorbed. In general, it has been shown that resonance among charged structure lower the energy of both the ground and as well as the excited states. Charged structures, however, stabilize the excited state more than they do the ground state. Larger the number of electrons involved in the resonance, smaller is the energy differences between the ground state and excited state. From the above discussion, it follows that more extended the conjugation in the molecule, greater is the contribution of charge structure, smaller is the energy difference between the ground state and the excited state, and hence longer is the wavelength of absorption. When this wavelength of absorption is long enough to lie in the visible region, we observe color. For example, ethylene 1,3-butadiene, 1,3,5-hexatriene, 110 diphenyl, 1,3,5,7,9 decaptane. It may, however, be remembered that the color of compound is actually the complementary color of light absorbed. Further, the presence of both electron donating groups or electron withdrawing groups at the end of conjugated system will extended the conjugation and will decreases the contribution of the charge structure towards the resonance hybrid. Consequently, the wavelength of the light absorbed becomes longer, and when this wavelength lies in the visible region, the compound appears colored. For example, colorless compound 204 nm, colorless steric effects and the colors. We know that the resonance is maximum when the system is completely or almost completely planar. If due to the steric hindrance resonance is inhibited, the depth of color will distinguish or the compounds may even become colorless. Molecular orbital theory. According to MO theory, whenever a molecule absorbs a photon of light, one electron is transferred from bonding orbital to the anti-bonding orbital. Depending upon the types of electrons present in the molecule, different types of electronic transitions are possible. A transition in which a bonding sigma electron is excited to an anti-bonding sigma orbital is called sigma sigma star transition. In the same way, the pi pi star represents the transition of a bonding pi electron to the anti-bonding pi star orbital. A pi-pi transition represents the transition of one electron of a lone pair, that is non-bonding pair of electrons, to an anti-bonding pi star orbitals. This type of transition occurs in the molecule containing double bonds involving heteroatoms: carbon oxygen bond, carbon sulfur bond, carbon nitrogen double bond, and may be represented as follows. These types of antibonding: the relative energies of these transitions are these types, shown these types. Of all these transitions, only pi star and n pi star transitions lies in the ordinary UV region. Further, more pi star transitions are much more than intensities than pi star and pi star transition, and hence are responsible for the color. Further, as conjugation increases, absorption due to the pi star transition gets shifted to longer wavelengths and ultimately to the visible region, and hence is responsible for color as explained below. In ethylene, there are two types of transitions, that is sigma star and pi star. The longest wavelength band, that is pi star, absorb at 175 nanometer. Since this band also lies in the far ultraviolet region, therefore the ethylene is colorless. Butadiene has lambda max at 200 217 nanometer due to the pi star transition. Thus conjugation has shifted the band to longer wavelength and the intensity has greatly increased. This may be explained as follows: a double bond consists of two pi star, one bonding to the other antibonding, but when two double bonds are brought into conjugation, four MOs are formed. 4 MO diagram is formed of these. That is, pi 1, pi 2 are the bonding of occupied by a pair of electrons each, while the other two are antibonding, that is pi 3 star, pi 4 star, as shown in figure 8.2. Thus, it is clear that the energy of highest occupied molecular orbital pi 2 is increases, while that is of the lowest unoccupied molecular orbital pi 3 star decreases. As a result, the energy levels involved in the pi star transition now become closer, and hence lesser amount of energy is needed. In other words, the energy gap between pi 2 and pi 3 star orbitals in 1,3-butadiene is much lower than in the corresponding energy gap in the pi star orbital in ethylene, and hence 1,3-butadiene absorbs at a longer wavelength than ethylene. Further, since the energy levels come closer, their interaction in the excited state increases, and hence epsilon max as also goes up. In a similar way, we can show that where three double bonds are brought into conjugation, the energy gap between the HOMO and LUMO becomes still smaller, and the wavelength of pi star absorption band increases, and when it reaches a visible region, color will appear in the compound. For example, the polyenes with n value of 6 absorption band occurs the blue region, and so the compound is yellow. Similarly, beta carotene absorbs in the greenish blue region, and hence the orange color. Now let us consider the benzene. It absorbs at 254 nanometer and is therefore colorless. Similarly, naphthalene and anthracene are colorless. As the number of fused rings increases, the position of absorption approaches the visible region. Thus, naphthalene will, with four linearly fused rings, absorbed in the blue region and hence is yellow, while pentacene, which absorbs orange light, is blue. Dyes. A dye is a colored substance which can be applied in solution or dispersion to a substance such as a textile, paper, leather, hair, for plastic material, wax, a cosmetic basis, giving a colored appearance. Condition which a dye is must satisfy: a substance can be used as a dye for the textile one of it is satisfied the following conditions: it must have a suitable color, it must be able to fix itself or capable of being fixed to the fabric from the solution. When fixed, it must be fast to light, resins to the action of water, soap, detergents, etc. during washing, or to the organic solvents during dry cleaning, etc. Nomenclature. The chemical names of dyes are very complicated and hence trade names are more popular. These trade names often include one or more alphabetical letters and and a number, whereas the number indicates the shade. Alphabetical letters refers to color. For example, G for yellow, R for red, and sometimes alphabets may also refers to some specific properties. For example, V WE for fast to washing. Sometimes the letter also stands for the intensity of color. For example, 6B stands for the deep purple color, but sometimes these letters may have entirely different meanings. For example, alizarin blue D. Here D stands for the direct, which means it is a direct dye for cotton. Classification of dyes. Dyes may be classified into a number of ways discussed below. Natural and synthetic dyes. Since early times, man has been trying to extract dye from the plants for using them to beautify his clothes. Such dyes are known as natural dyes. Two examples of natural dyes known since early times are indigo and alizarin. India has been the main producer and the exporter of indigo. However, natural dyes have only limited shades, hence, nowadays, most of the dyes used are the synthetic dyes, which can have a variety of shades. Most of these dyes are aromatic compounds obtained from coal tar, hence, these are also called coal tar dyes. Classification of dyes based on their constitution. In this system, dyes are classified on the basis of chemical constitution or the functional group to which the dyes owe their color. Some important classes are azo dyes, nitro dyes, nitroso dyes, triphenyl methane dyes, anthraquinone, dyes, indigo dyes, indigoid dyes, phenethylene dyes, acridine dyes. Classification of dyes based on their application. The application of dyes on a particular fiber depends on the nature of both the fiber and the dyes. There are four different ways in which a dye molecule may be attached to the fiber: through covalent bond, hydrogen bond, ionic bond, and the van der Waals forces. Based upon the method of application, dyes have been classified into the following categories. Acid dyes. The sodium salt of azo dyes containing sulfonic acid and carboxylic acid groups are called acid dyes. These dyes are applicable to the fabric from their acid solutions, and they are used to a dye wool, silk, nylon, and polyurethane fibers. The affinity of acid dyes for nylon is higher than that for other types, since polycarpolactam fibers containing a higher proportions of free amino groups. These do not have affinity for cotton and hence cannot be used to dye cotton. Typical example of acid dyes are orange 1, orange 2, methyl orange, and Congo red. Orange 1 is versatile dye prepared by coupling diazotization sulfide acid with alpha naphthol. The dye orange 2 is similar, obtained by the coupling diazotized sulfonylic acid with beta naphthol. When diazotized sulfonic acid solid salt is react with beta naphthol, then in the presence of removing of HCl, orange 2 is formed as a compound product. The structure and the chemistry of methyl orange and organo red will be discussed later in this unit. Basic dyes. These dyes are the salt of colored bases containing amino groups and has as the oxochromes. These includes azo and triphenyl methane dyes. In the acid solution, these amino groups forms water soluble cations, which then reacts with the anionic sites present on the fabric and thus get to the attached to them. Modified or reinforced nylons and polyester can be dyed with these dyes. Some common example of this class are aniline yellow, butter yellow, and cryosydine G, and malachite greens. Aniline yellow, butter yellow, and chrysodine. Chrysodine G is the orange dye and is obtained by the coupling benzene disonium chloride with the metaphenyldiamine. It is generally used to dye silk, wool, cotton, leather, and paper. Direct or substantive dyes. These are the water soluble dyes, as the name suggests. These are those dyes which can be directly applied to the fabric from the aqueous solution. These are most stable for fabric which can form hydrogen bond with the dyes. Thus, these are usually used for dyeing cotton, wool, silk, rayon, nylon, Congo red, and materials yellow are two well-known example of this class of dyes. Materials yellow, dispersed dyes. These are water-insoluble dyes and are applied to the fabric in form of a dispersion of the finally divided dye in a soap solution in the presence of some stabilizing agent such as phenol, cresol, or benzoic acid. These dyes are used to dye synthetic fibers such as nylon, polyester, and polycrylonitrile fibers. These dyes belong to the class of anthraquinone dyes and are suitable for dyeing synthetic polyamide fibers. Important example of disappear dyes are Keratin Fast Pink B, and Keratin Pink Fast Blue B. Fiber reactive dyes. These are those dyes which contains a reactive group which combines directly with the hydroxyl or amino groups of the fiber because of the formation of permanent chemical bonds between the fiber and the dye. The color of the dyed fabric is fast and has a long life. Cotton, wool, and silk can be dyed with these type of dyes which are derivatives of 2,4-dichloro-135 triazine are important example of fiber reactive dyes. Ingrain dyes or insoluble azo-dyes. These constituents about 60% of total dyes used. These are obtained by coupling of phenol, naphthol, arylamines, aminophenols absorbed on the surface of a fabric with a disonium salt, as there is only surface absorption of the dye on the fabric. The color is not fast. These dyes can be used to dye cellulose, silk, polyester, nylon, polypropylene, poly, polyurethanes, polycyclonitriles, and leather. An example of this type of dye is para red. When para-nitrobenzene disonium chloride is react with beta-naphthol in the presence of NaOH and removal of HCl, then para-red is formed as a product. Azo dyes also find used in foodstuffs, cosmetic, drugs, biological stains, such as indicators in chemical analysis. However, because of their toxic nature, these dyes are no longer permitted to dye foodstuffs. Wet dyes are insoluble in water and hence cannot be used directly for dyeing. Therefore, they are first reduced to a soluble colorless form in the large vats with the reducing agent such as an alkaline solution of sodium hydrosulfate. Under these alkaline conditions, the lysoform develops affinity for cellulose fiber. Therefore, these dyes are mainly used to dye cotton fibers. When indigo is reduction and oxidation by lysoform is formed as a product, the cotton fiber to be dyed soaked in the this alkaline solution and then oxidized to the insoluble colored form by exposure to air or by some oxidizing agent such as chromic acid and perboric acid. A well-known example of wet dyes is indigo. Indigo sol O ortho, on the other hand, is readily soluble in water. It has affinity for cellulose and can be rapidly and quantitatively oxidized on the fiber. With formation of indigo is especially suitable for wool. Mordant dyes. These dyes do not dye the fabric directly but require a mordant. The mordant in fact act as the binding agent between the fiber and the dye. For acid dyes, metal ions are used as a mordant, but for basic dyes, tannic acid is used as the mordant. These dyes are primarily used to dye wool. The fabric to be dyed is first solution soaked in the solution of a suitable metal salt, and the soaked fiber fabric is then dipped in the solution of the dye. When insoluble color complexes called lakes are formed on the fabric. In this way, the metal ions first get attached to the fabric, and then the dye molecules are linked to the metal ion through covalent and the coordinate bonds. The same dye can give lakes of different colors depending upon the metal ion used. For example, alizarin gives rose red color with aluminum ions, blue color with barium ions, brownish red with chromium ions, violet with magnesium, and red with the strontium ions. Azo chemistry important dyes. Azo dyes constitute the large class of synthetic dyes. They are chromophore as aromatic, that is aromatic system joined to azo group. The common oxochromes, amines, Nr2 and OH alcohol, etc. The usual method of preparation of azo involves direct coupling between a diazonium salt and a phenol or an amine. The structure of azo is elucidated by reduction with SnCl to HCl or sodium hyposulfate. When azo groups is repurchased with the formation of primary amines, which are then identified. Azo dyes are classified according to the number of azo groups in the molecule, that is monoazo, diazo, triazo. They are classified as basic dyes, acid dyes, etc. Two important dyes. Azo dyes are described below. Methyl orange, halothane. Synthesis methyl orange is obtained by coupling N-dimethylene with diazotized sulfonilic acid. Properties: it is the acid dye for wool and silk, but it is colored fades on exposure to light and washing. Therefore, it is not used as a dye but is better used as an indicator in acid base titration. It is yellow in basic solution, pale red in acidic solution. The changing of color is attributed to the changes in the structure of the ion. In the basic medium, the ion contains the azochromophore, while in the acidic medium it contains paraquinidine chromophore. Congo red is an example of diazodise that is contains two azo groups. Synthesis. It is obtained by the coupling tetraazotized benzidine with the two molecules of naphthenic acid. When naphthenic acid is treated with the tetraazotized with benzidine, then naphthalene acid is formed by coupling and Congo red is formed as a product. Benzidine needed for the purpose of many prepared by rearrangements of hydrobenzene in presence of acidic hydrogens. Entrance is prepared from the nitrobenzene by reduction with Zn and NaOH. Nitrobenzene is treated with in the presence of zinc and sodium hydroxide is reduced reduction by reduction the hydrobenzene is formed, and by hydrolysis the benzidine is formed as a product. Properties: it is direct dye and its sodium salt dyes cotton a full red. However, it is not a good dye but because the color changes when the acid is added. Therefore, it is used as an indicator. It is blue in acidic solution and red in solutions. This change in color from red to blue is acid is solution is due to the resonance among the charged canonical structure as follows. Triphenylmethane dyes. Triphenylmethane dyes are the derivative of triphenylmethane containing amine groups, Nr2 groups, and OH groups in their rings. The compounds so obtained are usually colored and are called lusobase. These, upon the oxidation, are converted into the corresponding colors, tertiary alcohol or carbonyl bases. These carbonyl bases readily change from the colorless benzoide forms to the colored quinidide forms in the presence of acid due to the salt formation. These changes are summarized below. Lysobase is oxidized and reduced when the carbonyl basis is formed as a product. When carbonyl basis is acid reacts with acid and alkyl and then dye is formed as a product. Some important triphenyl methane dyes are discussed below. Malachite grains. Malachite grains. The name of malachite grain is given to this dye because it deep blue-green color resembling that of malachite and an ore of copper. Synthetic, it is prepared by condensing N dimethylene with benzaldehyde at the 373 Kelvin temperature in the presence of concentrated H2SO4. The litho base or produced is oxidized with the lead dioxide in the solution of acetic acid and HCl. The carbonyl base is so produced reacts with the excess of HCl to form malachite grains. When benzaldehyde reacts with the N dimethylene, two molecules in the presence of H2SO4, then base is formed as a product. Properties: malachite grains dyes wool and silk directly and cotton moderate with tannin. The color of malachite grains fades slowly when strong acid and bases are added to it. The base causes the color to fade because it converts the dye back to the colorless carbonyl bases. However, in the case of acids, H positive ions combines with the lone pair of electrons present on the N atom of the free dimethylamino groups. As a result, chances of resonance decreases and the color fades. Crystal violet synthesis, it is prepared by heating either N dimethylene with carbonyl chloride or by heating Michels ketones with dimethylene. Dimethylaniline is in presence of POCl3. In the first case, Michels ketones initially formed condense further with the dimethylaniline to form crystal violet. When dimethylaniline is reacts with phosgene, then the Michels ketones is formed as a product. Properties: a weakly acidic solution of crystal violet is purple, a strongly acidic solution is green, and still more acidic solution is yellow. These color changes may be explained as follows. In weakly acidic solution, crystal violet exists as a singly charged ion. In the structures, two-thirds of the changes can oscillate in the horizontal direction. In strongly acidic solution, crystal violet exists as doubly charged ions. Here, the whole unit of charge can oscillate in the horizontal directions. The oscillation of and hence the color depends upon the purple to depends to the purple to green in very strongly acidic solution. Another proton is added to form triply charged ions. In this ion, only little resonance is possible and hence the color lightens from green to yellow. Uses: crystal violet is used in the manufacture of ink, stamping pads, and the typewriting ribbons. It is also used as an indicator for determining hydrogen ion concentration in solutions. Phthalate dyes. These are obtained by considering phenol with the phthalic anhydride in the presence of certain dehydrating agents such as concentrated H2SO4, ZnCl2, and anhydrous oxalic acid. Phenolphthalein is a Phenolphthalein is a phenolphthalein dye. It may also be regarded as a triphenyl methane derivative synthesis. It is prepared by heating phthalic anhydride with the phenol in the presence of concentrated H2SO4. Phthalic anhydride is heated with in the presence of concentrated H2SO4. Then phenolphthalein is formed as a product. Properties. Phenolphthalein is not a dye. It is insoluble in water but dissolved in the alkalis to form deep red solution. This is due to the formation of disodium salt, which undergoes resonance and has quinidide structures with excess. When excess of strong alkali is added, the solution of phenolphthalein becomes colorless again due to the loss of quinidide structure and the resonance as follows, shown below. Phenolphthalein, when oxidized and hydrolyzed, then it changes its color red to the colorless. Uses. Because of the color changes shown below, the phenolphthalein is used as an indicator in acid-base titration. It is also a powerful laxative. Fluorescence. Fluorescence. It is a xanthetic derivatives in the preparation of properties. It is more closely resemble phthalic dyes synthesis. It is prepared by heating phthalic anhydride with resorcinol at 473 Kelvin temperature or at 383 to 393 Kelvin temperature with anhydrous oxalic acid. When phthalic anhydride is heated with resorcinol in the presence of anhydric oxalic acid, then fluorescein is formed as a product. Properties. It is a red powder insoluble in water since it is colored, therefore the non-quinidide uncharged structure 1 is not satisfactory to account for the red color. Two quinidide structure as possible in which the conjugation is totally different, one having the paraquinidide structures and the other orthoquinidide structures. Fluorescein is dissolves in the alkalis to give a reddish brown solution. On the dilution gives a strong yellowish green fluorescence due to the formation of anion. Sodium salt of fluorescein is known as the uranine. The dye is wool and silk yellow from an acid bath. The color are however fugitive. Eosine is a tetrabromofluorescein and is obtained by the action of bromine on fluoresceins in glacial acetic solution. When fluorescence is reacted with in the presence of acetic acid, then eosine is formed as a product, and since eosine is a red powder, so its structure cannot be matched. Eosine dyes wool and silk pure red. The yellow fluorescence is in the case of silk. Eosine in the form of lead lake called vermilion is used for poster printing. Most of the red inks are dilute solution of eosines. Alizarin. Alizarin is one of the most important anthraquinidide. It occurs in the madder root in the form of its glucosides called rubberic acid. When rubberic acid is reacts with water in the presence of enzymes, then alizarin and glucose is formed. As alizarin is 1,2 dihydroxyanthraquinone structure. This structure is the alizarin. It has been discussed as follows. Elemental analysis and molecular weight determination have shown that the molecular formula of alizarin is C14H8O4. On reduction with zinc dust at 673 Kelvin temperature, alizarin gives anthracene. This implies that the alizarin is a derivative of anthracene. With acetic anhydride, alizarin forms a diacetic, thereby suggesting that alizarin contains two hydroxyl groups. Alizarin can be prepared by condensing phthalic anhydride with the catechol in the presence of concentrated H2SO4 at 453 Kelvin temperature. This shows that alizarin in a dihydroxy derivatives of anthraquinone in which both the OH groups are present in the same ring. When phthalic anhydride is react with catechol in the presence of H2SO4, then alizarin is formed as a product. On the basis of the above condensation reactions, the following two structures are possible for the alizarin, structure 1 and structure 2. Alizarin on the nitration gives two isomeric mononitro derivatives, both of which on oxidation gives phthalic acid. This suggests that in both cases, both these nitro derivatives and NO2 groups is present in the same ring, which contains the hydroxy group, since structure 1 and has two different positions available for nitration. Therefore, it can give two different nitro derivatives. Structure 1, on the other hand, can give only one nitro derivative, since the two vacant positions are equivalent. Since structure 1 can explains the formation of two different nitro derivatives, therefore the actual structure of alizarin it is 1,2-dihydroxyanthraquinone, and note the structure 2, that is the 2,3-dihydroxyanthraquinone. Manufacture, it is manufactured by sulfonating anthraquinone with fuming sulfuric acid at 413 Kelvin and fusing the sodium salt of product anthraquinone to sulfonic acid with NaOH containing a calculated quantity of sodium or potassium chlorate at 453 to 473 Kelvin under pressure. Acidification of the product with dilute HCl gives alizarin. The function of sodium or potassium chlorate is to provide oxygen for the oxidation of carbon hydrogen bond and carbon oxygen OH bond. When anthraquinone is heated with the react with the in the presence of H2SO4 sodium SO3 at Kelvin at 413 Kelvin temperature, then anthraquinone 2 sulfonic acid is formed as a product, and and finally the alizarin product is formed as a product. Anthraquinone needed for the purpose can be prepared from benzene and phthalic anhydride as follows. When phthalic anhydride reacts with benzene ring in the presence of anhydrous AlCl3, Friedel-Crafts acylation form the product orthobenzol benzoic acid, and by in the presence of concentrated H2SO4 and the removal of H2O in the water, anthraquinone is formed as a product. The properties: alizarin forms ruby red crystal melting point at the temperature 563 Kelvin temperature. It is insoluble in water and alcohol but dissolves in the alkalis to form purple solutions. It is sublimes on heating. It is moderate dye and the color of lake depends on the metal used. Aluminium gives a red lake. Ferric salts gives violet black, while chromium salt from brown violet lake. Aluminium and into the lake are usually employed for the cotton dyeing and printing, while aluminum and chromium lakes are used for wood dyeing. Oxidation: on oxidation with MnO2 and H2SO4, it gives purpurine. When alizarin is reacts with the oxidized with the MnO2 and H2SO4, then purpurine is formed as a product. Reduction: on the reduction with zinc dust and the ammonium hydroxide, it forms anthraorbin. Alizarin is used as a mordant dye and also as purgative dyes. Indigo: India is the birthplace of indigo, its official name being indigotin. It is oldest wet dyes known. Egyptian mummies' clothes 5,000 years old were dyed with it. It occurs as an indicator which is the glucosides of the indigoxyl in Indian paint, indigofera, tino tinctoria, and the European plants Stasis tinctoria, and the indication on hydrolysis with ether, HCl, and enzymes gives indigoxyl, which upon aryl oxidation gives indigotin. When indican is heated with the dilute HCl and enzymes in the presence, beta glucose is formed as a product and then oxidize indoxyl compounds in the acetyl oxidation, and the indigo is formed as a product. Structure. The structure of indigo has been deduced as follows. Elemental analysis and molecular weight determination have shown that the molecular formula of the indigo is C16H10O2N2. Fusion of the indigo at low temperatures produces anthralonic acid. Indigo, when indigo is fused NaOH presence, then it forms products. This suggested the indigo contains one ortho substituted benzene ring in which the one position is attached to a carbon atom while the other is linked to the nitrogen atom. Oxidation of indigo with HNO3 yields two molecules of styrene, suggested that indigo contains two identical units joined together and that each unit on oxidation produces a molecule of styrene. When indigo is oxidized, then styrene is formed as a product. The structure of acetine has been confirmed by its synthesis is sketched below. Then orthonitrobenzoyl chloride is treated with in the presence of NaCN, then hydrolyzed, and then in the presence of FeSO4 NH3 formed as styrene as a product. On the basis of structure of acetine, the following three structures 1 and 2, 3 are possible for indigotine. Indigotine on the treatment with dilute alkyl yields anthranoic acid and the indicooxyl 2 aldehyde is formed as a product. Formation of indoxy 2 aldehyde suggested that the two identical units in indigotine are connected through positions 2 of indigooxyl moiety, while position 3 carries an oxygen containing functional group. These arguments suggest that most probable structure of indigotine is 1. Further X-ray analysis has revealed the indigotine has the more stable trans configuration. Its structure has been confirmed by these following three syntheses. Humans first indigo synthesis, condensation of aniline with chloroacetic acid produces N-phenylglycine. This, upon fusion with NaOH and NaNH3, NaNH2 at 523 Kelvin temperature gives indoxyl, which upon subsequent oxidation by air gives indigotine. When aniline is treated with chloroacetic acid, heated with, and the N-phenylglycine is produced, then the NaOH in the presence of NaOH and NaNH2, the indoxyl formed as a product. The yield of indigotine is low. To improve the yield, a modified method of preparation of N-phenylglycine was used, which is described below. Formaldehyde is at the presence of NaHSO3 at 323 to 353 Kelvin temperature. Then, in the presence in the by the hydrolysis, the N-phenylglycine is formed as a product. Human second indigo synthesis. This involves the condensation of anthracyanonic acid with the chloroacetic acid to form N-phenylglycine orthocarboxylic acid. This, when fused with the KOH and NaNH3, NaNH2 produces indigooxylic acid, with which subsequently undergoes dicarboxylation to form indoxyl aryl. Oxidation of indoxyl finally gives indigotine. For from aniline and the ethylene oxide. Aniline on treatment with the ethylene oxide forms N-phenyl beta hydroxyl ethylamine, and this upon fusion with the mixture of NaOH and KOH at 473 gives the corresponding sodium potassium alkoxides. With the sodium potassium salt is heated with the sodiamide. This is then dehydrogenated on heating rapidly to 573 Kelvin temperature and on rapid cooling to 578 Kelvin temperature. Ring closure occurs to form sodium potassium salt hydroxide the upon treatment with the water oxidation by air gives indigotin is formed as a product. It may be noted that synthetic indigo is much cheaper than natural indigo. In fact, synthetic indigo has virtually whipped virtually whipped out the indigo plantation so popular at one time in India. Properties: indigotin is a dark blue powder with the coppered illustrate melting point 663 Kelvin temperature. It is insoluble in water and most organic solvent. When a paste of indigotin is agitated with alkaline sodium hyposulfate in the large vats, the insoluble indigotin is reduced to the soluble LUSO compounds called indigotin white. An indigotin blue is reduction and oxidized, then indigotin white is formed as a product. The cloth to be dyed is soaked in this alkaline solution and then exposed to air. When the original blue color is regenerated on the cloth, uses indigo is extensively used for dyeing cottons. The quality of color is excellent and is stable to the lightning and washing etc. It is used in the printing links. So, thanks for watching, guys. Thank you.